I'm Eric Shidley, and this is Astronomy Fundamentalized, Lecture 5, Lunar Observations. In this lecture, I'll describe the moon phases and their cause, and also suggest a way that we can tell the time of day simply by looking at the moon. This very striking animation is a sequence of photos taken of the moon throughout the course of the lunar cycle, or the lunar month. It takes the moon about 29 and a half days to orbit the Earth, and in that time, the way it appears from the surface of the Earth undergoes remarkable changes. We're all familiar with the lunar phases. We see the moon as full, and then first quarter, third quarter, new. We see it as crescent, we see it as gibbous, all these different moon phases, which I'll describe in a moment. But there are some remarkable features to this image here that I'd like to point out. One is that we can see that the angular size of the moon changes throughout the lunar month. The actual sphere that is the moon, or the circular disk here that we actually observe, is getting larger and smaller. This is because during the course of the month the moon gets closer to and further away from the Earth, and that changes its angular size. Even more remarkable still is that the moon here appears to show its same face towards the Earth at all times. We never see the moon turn around so that we can see the opposite side. And there is a little bit of fluctuation. The moon seems to wobble in showing the same face toward us. The reason for this is that through very, very, very long time scale, the Earth has been exerting tidal forces on the moon that has locked the moon's orbit so that it always shows one face towards the Earth. Indeed, the moon looks remarkably spherical if you just look at it up in the sky, but in fact it is not uniform in the distribution of its mass. So the Earth exerts different gravitational forces on different regions of the moon, which causes a tidal force, which has caused this effect, which is sometimes referred to as tidal locking. The vibrating behavior is known as lunation. Nevertheless, the moon always shows the same face to the Earth. As I mentioned in the previous lecture, it's like the moon goes around the Earth as a cameraman, always pointing towards the Earth in its orbit. As far as phases go, here I am looking south at the southern sky at sunset. Now, on any given day of the month, I can see the moon in the sky. If it's a full moon that I'm looking for, then at sunset, on any given day, a full moon would be rising in the east. The full moon actually spends most of its time up during the night, and in fact, the full moon is at its highest point in the sky at midnight. As I continue along through the arc in the sky here, we see that I get differing moon phases. I should actually start on the right-hand side of the diagram where it is a new moon. The new moon is just setting at sunset. That means that the new moon has been up all day. So this new moon is in the sky as you're going about your daily activities, but you don't see it for two very good reasons. The new moon is entirely dark in that it is not reflecting any of the light of the sun back to the Earth, so even if the sun were down, it still wouldn't be visible. And so I can just catch this first crescent of the moon's reappearance on the western horizon as the sun sets. We call this a crescent moon, and as I proceed from right to left on the diagram, the moon becomes more and more crescent. We say that the moon is waxing crescent as it gets fatter and fatter. At sunset, which is approximately 6 o'clock, I'll see a first quarter moon. Where the moon is 1 week through the 4-week cycle, I'll see the first quarter moon directly south. As I continue on, the moon goes from being a first quarter moon to getting fatter and fatter and fatter and fatter. This is called a gibbous moon, and it's getting more and more gibbous as time goes on. Gibbous comes from the Latin word for humpbacked. And so the moon is getting gibbous, gibbous, gibbous until ultimately the full moon is 2 weeks through its 4-week cycle. Now, just going out and observing the moon, keeping, let's say, a moon journal, and recording how the moon looks at what time of day, this is an easy observation to make. It's a little bit more difficult, particularly for ancient astronomers, to explain why it should be so that the moon looks this way. In order to completely understand the moon phases and their behavior, we need to understand how moon phases depend on the relative position of the moon, the Earth, and the sun. Here I have a diagram of the Earth as viewed from above. We're looking down on the North Pole. Imagine then that you're standing on the right-hand side of the Earth labeled noon. If you're in this position, the sun is directly overhead, and the yellow arrows on the right-hand side of the diagram indicate the rays of the sun shining on the Earth. As the Earth rotates in this diagram, it would rotate in a counterclockwise direction. And that makes sense, because if you're standing at the position of noon, you will rotate to 3, you will rotate to 6, where the sun will set and become obscured by the surface of the Earth. You'll rotate to 9, to midnight, to 3, to 6, and then at 6 a.m. the sun will rise again, 9 a.m. noon. Now, of course, the rise and set times of the Earth are variable throughout the seasons, being at the northern latitudes, and the angle of the axis of the Earth's rotation compared to the plane of the Earth's orbit. Nevertheless, it's roughly around 6 a.m. that the sun rises and roughly 6 p.m. that the sun sets. We also see in orbit around the Earth the moon in several different positions. Here we see 8 moons. There aren't 8 moons. This is the same moon in 8 different positions. If we imagine that the moon was in the rightmost position, the one that's labeled new, then the only way that we could see this moon is if we were standing on the surface of the Earth somewhere between 6 a.m. and 6 p.m. If we're on the far side of the Earth between 6 p.m. and 6 a.m., this moon is obscured by the Earth itself and is impossible to see. This moon is called the new moon, and in fact, we don't see it illuminated by the sun because the sun is behind it. You might immediately think, well, isn't this an eclipse then? We'll cover eclipses in the next lecture. It turns out it's a little bit trickier to get an eclipse because this does not represent the actual scale of the situation. Remember that if the Earth is the size of my fist, then the moon is the size of my thumb 3 meters away. So this diagram's not to scale, so we don't need to worry about any eclipses at this point, but the moon will move along in a counterclockwise orbit around the Earth. So we'll go from the new position to the waxing crescent position. In order to see the waxing crescent, we would have to be on the surface of the moon somewhere between 9 a.m. and 9 p.m. That is, pardon me, the waxing crescent moon will rise at 9 a.m. and set at 9 p.m. Because of the way that the sun is partially illuminating viewed from the surface of the Earth, the rightmost portion of the moon, then we see a bit of a crescent. As the moon moves on in its counterclockwise orbit to the first quarter, we would see this phase of the moon between noon and midnight, because those are the positions on the surface of the Earth where you can actually have line of sight to see this first quarter moon. That means that the first quarter moon rises at noon and sets at midnight. Following the same logic as the moon continues in its orbit around the Earth, you see that the waxing gibbous rises at 3 and sets at 3. That is, it rises at 3 p.m. and sets at 3 a.m. The full moon rises at 6 p.m. and sets at 6 a.m. The full moon is up all night long. The waning gibbous rises at 9 p.m. and sets at 9 a.m. And the third quarter rises at midnight and sets at noon. The waning crescent rises at 6 a.m. and sets at noon, and then we're back to the new moon again. Of course, there's a continuum of moons in between all of these as we go in successive days, day after day, the moon moving in its orbit, taking 29 and some odd days to go all the way around. Nevertheless, this relative positioning of the sun, the moon, and the Earth is what explains the phases. But it also gives me a unique opportunity. If I can carry this diagram around in my head, and the simple orientation and be able to label it up very quickly. I once drew this on the beach with a stick in the sand in order to demonstrate to people that this could be done. It's possible for me to estimate the time of day. Consider the following. Once again, I'm looking south, and I see the moon up in the sky. This is a waxing crescent. I know that it's waxing because I know that the shadow of the moon moves from right to left. And so this is going to be getting brighter and brighter as it goes. So this is a waxing crescent. I know that a waxing crescent moon rises at 9 a.m. and sets at 9 p.m., which means it should be directly south at 3 p.m., because 3 p.m. is midway between 9 a.m. and 9 p.m. If you have trouble coming up with that, just think of the face of a clock in your head. If I have 3 p.m. and if I have 9 a.m. and 9 p.m., what's in between? And the answer is clearly 3 p.m. If I look up in the sky and I see that the position of the moon is about 45 degrees from 3 p.m., that means it's about halfway between 3 p.m. and 9 p.m., which is 6 p.m. Well, you see that this method relies heavily on my ability to estimate the angular position of the moon relative to south. But remember that I have a handy scale where each palm width is 10 degrees, and so I can point my palm southward. I'll probably rely on my knowledge of the constellations in order to find, in order to direct in the southward direction. Opposite the pole star would be an ideal way to do that. And then I measure off the number of degrees over, and I can get the best possible measurement. Give it a try and see if you get close to the correct time of day.